Got it.
Hello and welcome to our seminar on optimization. It is my great pleasure to introduce our speaker today, who is Ting Kei Pong from the Hong Kong Polytechnic University. So Ting Kei received his bachelor and master degree in mathematics from the Chinese University of Hong Kong, and then he moved to the United States. He started his PhD at the University of Washington under the supervision of Paul Cheng, and after his disappearance, he was co-advised by Professor Faisal and by Professor Thomas. And then he received his PhD degree in 2011, and who was a postdoctoral fellow in Canada and different places. So first of all, at the University of Waterloo, and then at the University of British Columbia, where he worked together with Michael Friedlander. And in 2014, he started his position at the Hong Kong Polytechnic University, where Ting Kei is now associate professor. Ting Kei has many research interests, work in optimization on theoretical topics, on numerical methods. He has a very wide and important, consistent publication portfolio. Ting Kei, thank you for accepting our invitation. You have 45 minutes for your talk.
Okay. Yeah. Okay. So thanks, Radu, for the introduction, and also thanks to organizers for the invitation for me to give a talk here. So I'm going to talk about analysis and algorithms for compressed sensing models based on the ratio of L1 and L2 norms. So L1 is on the top, and then the L2 norm is the denominator. So this is a joint work with my former PhD student, Peiran Yu, who just graduated in August. And this is part of her PhD thesis. She's currently doing a postdoc in University of Pittsburgh, working on machine learning complexity, I think. And also with my current postdoc, Liao Yuanzheng. Okay. So we are looking at compressed sensing, which is really just the problem of finding sparse solutions of linear systems. And there are a lot of models for compressed sensing, and this is just one of the many models that you can consider. Okay, trying to minimize some sparsity-inducing regularizer. A very classical choice would be L1 norm. And here we are looking at equality constraints. Well, I'm basically thinking of B to be having no noise here. And my A would be the measurement matrix. And here and throughout the whole talk, A would always have full row rank. So the feasible region, A inverse B, would be non-empty. And I also assume that B is not 0 for the noiseless model, because otherwise the problem would be trivial. 0 would be the solution. And of course, in practice, there would be noise in the measurements, let's say Gaussian noise. Then it is quite common that people would consider this kind of constraint model, where we have the norm of AX minus B being bounded by sigma. It is also quite common that people consider this 2 norm, but they square it and put it into the objective as a regularization term, and making the problem an unconstrained optimization problem. But today, I'll be more interested in this kind of constrained formulation, because, well, this kind of sigma somehow allow us to explicitly control or sort of reflect our tolerance or preference on the deviation of A of X from B. So we sort of choose explicitly what we want to see, okay, by tuning the sigma. And of course, the sigma cannot be too large, because otherwise we will again be including the origin in the feasible region, and the problem would be trivial again. Now, are there other sparsity-inducing objectives? Well, of course, there are a lot. Well, many comes in the form of difference of convex functions like scared penalty or the MCP function, or some regularizers that are not really difference of convex functions, like the LP quasi-norm, where P is strictly between 0 and 1. Okay. And besides the Gaussian noise model, can we also consider other noise models? Now today, we'll be interested in L1 over L2 type models. Well, the use of the ratio of L1 and L2 norms for compressed sensing, to the best of my knowledge, dates back to Gaussian and his co-authors in 2014. And it has been extensively studied recently by Yifei Liu and her co-authors. And here is the model. Okay. And I'll refer to this as the noiseless model in this talk. Minimizing L1 over L2, subject to AX equals B. And here it is very important that B is not 0, because otherwise we'll be doing 0 over 0. Oh, haha. And recently, we replaced this equality constraint by an inequality constraint here, a single inequality constraint, in the hope that we will be able to cover some noisy model. So we assume that our Q is taking this form, P1 minus P2, where P1 would be Lipschitz differentiable, and P2 is convex, finite valued. Feasible region is non-empty, and again, the origin is not feasible. And these assumptions on Q are already general enough to cover several interesting noise models. Well, needless to say, we can work with the Gaussian noise model. This was the model that we saw two slides ago. Okay, so basically we put Qx less than equal to 0. That's the Gaussian noise model. Now, besides the Gaussian noise, we can also consider some heavy-tailed distribution, Cauchy noise. Now, when it comes to the Cauchy noise, it is quite common that people consider this function, which is called the Lorentzian norm. Although this thing is definitely not a norm, but that's how they call it. And this is really coming from the maximum likelihood estimation based on the Cauchy distribution. The gamma is basically the standard deviation of the underlying Cauchy. And when we put down the yi square here, we are sort of thinking of the Cauchy to have mean 0. And then the constraint again would be Qx less than equal to 0. Now these things fall under our framework because, well, Q is Lipschitz differentiable. So we can just take these functions to be P1 and our P2 will be just 0. Now there's another noise model we can consider, which would make use of a Nonzero P2, which is the sum of electromyographic and Gaussian noise. So this would be some really huge noise that you can just think of those as outliers, and you might just want to throw those particular entries away. And we make use of this function, where S is the set of R sparse vectors. So this is the L0 norm. Okay. So if my AX minus B is in S, it would mean that AX minus B is R sparse. At most, R's entries are non-zero, and those would be the outliers, sort of. Now, if I require Qx to be less than or equal to 0, well, I'm not really requiring AX minus B to be exactly in S, but only approximately in S, in the sense that the sum of squares of the tail would be bounded by sigma square. Okay, and then the tail, you can think of that as sort of the Gaussian part. Now, this function is not differentiable, but it still falls under our framework because you can rewrite the distance function as the minimum. And then you can expand this quadratic, and then we get this nice function here, which is nicely Lipschitz differentiable. This is our P1. And then we'll be subtracting the max of some functions that are affine in X, which would be P2. This is convex. And it is also finite valued because P1 and Q are. Now, let me also point out that a subradiant of P2 is pretty easy to compute. You just need to compute AX minus B, and then you project onto S, which is just a sorting and truncation. And then you multiply by A transpose, multiply by 2. So this would be important when we get to the numerics. So the L1 over L2 models, they are motivated from the spherical section property, SSP, which is one of the several sort of famous recovery conditions from the compressed sensing literature. So I will talk a little bit about this condition in the next slide. Now for the noiseless optimization model, under S null space property, well, this is yet another recovery condition from the compressed sensing literature. It was shown that any S sparse solution of the linear system is a local minimizer of the L1 over L2 optimization model. So at least it looks like trying to minimize the noiseless model seems to be a valid approach. Okay. And then there's a Dingleback type algorithm proposed for the noiseless model with subsequential convergence established in the sense that any accumulation point of x of t would be stationary for the noiseless model. And I'm saying that this is a Dingleback type algorithm because, well, when you look at this subproblem, we are not really making use of the quotient itself, but rather we are making use of the numerator, and then we are subtracting, well, sort of the denominator, but okay, we majorize it by linearization. Okay. Now, there are several questions. First of all, we are optimizers, right? And we are trying to minimize L1 over L2, which is not even level bounded. So are there really globally optimal solutions for us to look for? And then, well, we have a nice looking algorithm here, the Dingleback type algorithm, of this one. Okay. We know subsequential convergence. How about convergence of the whole sequence? And what's the rate? Finally, how about algorithm for the noisy case? Well, this is just the noiseless version. So in this talk, I'll be looking at these three problems. My main focus would be on point number 2 and number 3. So I will be quite brief on point number 1. Well, there's always a trivial answer to bullet point number 1. We can always intersect the feasible region with a huge compact set. And then now the feasible region is compact and we are minimizing L1 over L2, which is continuous on the feasible region. Well, the feasible region does not contain the origin. So problem solved. There will be globally optimal solutions. Well, except that we sort of slightly changed the model. So today I will be more interested in looking for conditions on A. Maybe I should make it bigger, on the A matrix. Okay. In the sense of those, in the flavor of those recovery conditions from the compressed sensing literature to guarantee solution existence. And the condition I'm going to make use of is the spherical section property, the SSP. So definition, we will say that a subspace has the SSP if the ratio L1 over L2 over all non-zero vectors in V is bounded below. Now, what is this condition doing? Well, for any k-sparse vector U, meaning that there are at most k non-zero entries, if you just apply the Cauchy-Schwarz inequalities to those k non-zero entries, you are going to get something like this. Okay, so you will get a square root k instead of square root m. Now, if you compare this inequality with this definition, then you can see that k is actually greater than or equal to m over s. Okay. So basically, the SSP is trying to impose a lower bound on the number of non-zero entries of non-zero vectors in V. And just like many of those conditions, recovery conditions from the compressed sensing literature, this thing is also generic. So if my A matrix has IID standard Gaussian entries, then the null space would have SSP with high probability, well, with suitable parameters. And then this is our result. So for the noiseless model, suppose that we have this generic condition, and suppose that the linear system really has a sufficiently sparse solution. Then the set of optimal solutions of the noiseless optimization model would be non-empty. If we are solving a reasonable problem, there should be a globally optimal solution. We also have a similar result for the noisy case. Now the proof is very standard, so I'm not going to go through it. It is basically based on standard asymptotic type analysis, and you immediately see the connections between this problem that I just boxed with the SSSP. We also have a similar result for the noisy model. Now, before moving on, I really have to confess that this is not really a recovery type result. Okay, I'm not saying that by solving the noiseless model, I'm getting the unique solution of the compressed sensing problem. I'm not. I'm just saying that the optimization model would have a non-empty solution set. Now, recently, there are really some recovery results proved by this group of researchers, and their paper is published in Applied and Computational Harmonic Analysis. And they also made use of SSSP, but they required a larger lower bound, and which is quite reasonable because under their condition, they can actually show that the compressed sensing problem, I mean, the linear system actually has a unique solution, and then solving the L1 over L2 would actually recover that unique solution. So our result here is of slightly different flavor. We only care about the solution existence of the optimization model. Ooh, okay, so this is the end of the first part of the talk. Now, in the second part, I'm going to talk about convergence rates of the Dinkelbach type algorithm for the noiseless model. Now, these days, when it comes to convergence rates, especially for first order method, almost inevitably, we will need to look at KL property and KL exponent. So just a review. So let H be proper closed, and let alpha be a number between 0 and 1, including 0, excluding 1. We will say that H has the KL property with exponent alpha at a point x bar in the domain of limiting subdifferential of H if locally, and well, in terms of proximity to x bar and also function value proximity, we have this inequality, which says that somehow we can bound the deviation of h of x from h of x bar to a certain exponent by the norm of the least norm element of the subdifferential of h at x. And if H has the KL property at every point in the domain of subdifferential, and if we can choose the alpha to be the same, then we will say that H is a KL function with exponent alpha. Now, because of the work by Botti, Atouche, and many other colleagues, we now know there are a lot of examples of KL functions. Proper closed semi-algebraic functions, they are KL with exponent alpha. Except that this alpha, in general, is pretty hard to determine given an optimization model. But on the other hand, there is a folklore type result saying that if alpha equals 1/2, then first order method would be locally linearly convergent. So it will be interesting to try to estimate alpha for a given optimization model. And bullet point number 2 is the main fact that we are going to make use of today. Piecewise linear quadratic functions, no matter convex or not, they are KL with exponent 1/2. And by piecewise linear quadratic, I'm just making use of the standard definition. Basically, the domain is a union of polyhedrons. And when you look at each polyhedron, you see a quadratic. And the function is continuous on the whole domain. That's the standard definition. Now, as I just said, determining explicitly the KR exponent is hard given an optimization model in general. And here, I'm basically trying to take the path that I have been working with Gaussian and also in the PhD thesis of my student, Peiran, that we'll develop some calculus rules to help us derive the KR exponent of functions that we don't know from those that we actually know the KR exponent. And I will introduce two calculus rules today. The first one is something like a quotient rule. Yeah, something like a quotient rule. Now, there are two objects of interest, capital G, which is the ratio of little f and little g, that's a quotient. And also this HUX, which I will just call this thing a difference function. So that's the difference between little f and little g with a scaling. Now notice that when we make use of this function later, okay, this u will be x bar, which is a stationary point of capital G. So that would be a point that is fixed. Okay, so this is really just a scaling. I'm not thinking of a function of u and x, but just a function of x. Now let f be proper closed and non-negative. And let g be a non-negative continuous function that is continuously differentiable on an open set containing domain f with infimum of g being positive over domain f. It looks very complicated, but when I wrote down all these assumptions, I was really just thinking of my g to be the square of the two norm. Okay, so if you don't want to remember all these clumsy assumptions, just think of g as the square of the two norm. And I also need one structural assumption on little f. My little f has to be h plus delta d. Okay, locally Lipschitz function h, and also the d would be non-empty closed set. Delta is indicator function, and h and d are subdifferentially regular everywhere in D. I'm not going to put down the definition of subdifferential regularity here. Just examples. Okay, convex stuff would work. Okay. And my h, you can safely think of my h to be the square of the one norm. You will know why I need to square it later. And the d is just the A inverse of B, okay, for the noiseless model, the feasible region of the noiseless model. Okay. Now, let x bar be a stationary point of capital G, the quotient of function. If the difference function has the KR property at x bar with exponents theta, okay, of course the u is chosen to be x bar as well, then G would have the same KR exponent at x bar. The exponents got transferred to G. Now, this is the second calculus rule I will need today, which is something like a power rule. Okay. I will call this a power rule. So let P be a proper closed function and let x bar be such that Px bar is finite and positive. Now, it's very important that this is positive, otherwise there will be counterexamples. Very easy counterexamples. Now, if P square satisfies the KR property at x bar with exponent theta, now you take the square root, you keep the exponent. You take the square root, you keep the exponent. Now, Px bar being positive is very important. Otherwise, you have trivial counterexample. Just think of x squared as 0. Oh, sorry. Now, this is the main result of the second part of the talk. So this function, well, this is really the objective of the noiseless model. And this is the indicator function of the constraint set of the noiseless model. So this function is KL with exponent 1/2. I'll actually show you the proof of this theorem number 4, which is actually not too hard given the 2 calculus rules that we already have. So this is what we want. We want the KR exponent of this function at x bar, let's say a stationary point. Okay, those are the only points that we care about the exponent. Now, because of the power rule, we can consider the squared version. Doesn't matter. Yeah, and the implication would work. Now, what is this function over here? Well, at least around x bar, well, because the feasible set does not contain the origin, x bar cannot be 0. So around x bar, the denominator is non-zero. So you can really think of this whole thing as a quotient, right? You can put this thing into the numerator. Okay, so now we have a quotient objective. So we apply the quotient rule. So instead of the quotient function, we could have considered only the difference function. Okay, the difference. And this difference function is piecewise linear quadratic. So it's 1/2. Everything is 1/2. Now, from this proof, is quite easy to see that. It should be easy to see that you can always replace this A inverse B by any polyhedron that does not contain the origin. So in particular, if you want to make the feasible set compact, you just, as long as you intersect with a polytope, you will preserve this KR exponent result. Now with the KR exponent result, we can state convergence rate result for the Dinkelbeck type algorithm. Well, except that I'm cheating a little bit by sort of assuming that we can somehow more or less accurately solve this problem. Yeah, the inexact version would be much harder to deal with. So yeah, so let's presume that somehow we can more or less solve this sufficiently accurately enough. Okay. Then we will have local linear convergence to stationary point. Now, I would like to point out that convergence of the whole sequence is not very surprising because F is semi-algebraic and it follows from very standard line of analysis. These days, we can look at these 2 papers. What I would like to emphasize here is the role of the KR exponent, which actually is the thing in violet. Yeah. Okay, so the first row, this is KR exponent being 1/2. Now the second inequality basically comes from the first order optimality condition of the subproblem. And then this second inequality is the sufficient descent property, which is again somehow a property of the underlying algorithm that we make use of. So it is really the first line, that is very closely related to the model. So this is the end of the second part of the talk. Yeah. Now, in the third part, I'll talk about the noisy model, an algorithm for the noisy model. It looks very wordy here, but okay, so this part is really the original thing I have written down for the noisy model, the same assumptions as before, okay? Except that now somehow, when we look at the QX less than or equal to 0, at least for the 3 concrete examples that we think of, this feasible set is not necessarily easy to project onto. So somehow we will need to play with Lagrange multipliers. And well, we better make some assumptions so that there will be Lagrange multipliers. So we also assume generalized MFCQ holds at every feasible point. This means that if Q of X is 0, then 0 is not in the Clark subdifferential of Q at X. Well, this assumption is actually not too restrictive because we can actually show that this condition holds for all our 3 choices of Q that correspond to the Gaussian noise model, the Cauchy noise model, and also the sum of the electromyographic and the Gaussian noise. Now, what algorithms should we use for this problem? Well, there are lots of possible choices. For example, augmented Lagrangian. And today, I would like to look at some feasible type method, which would try to maintain the sequence inside the feasible set. At least I try to avoid the origin. And our algorithm would be based on the moving balls approximation technique. Now, moving balls approximation algorithm was first proposed in 2010 by Oslander, Sheffy, and Tabu. And it was originally designed for this class of very classical and general nonlinear programming problem where f and gi are basically just C1. And here for the ease of exposition, let's say Lipschitz differentiable. And this is the key update of the moving balls approximation algorithm, the MBA algorithm. So in each iteration, we start feasible. And then we compute the next iterate as the unique minimizer of this strongly convex subproblem, where the LF and the LGI are the Lipschitz continuity modulus of the gradient of F and the gradient of GI, respectively. So you can see that the objective of the subproblem is a majorant of the original objective at x of t. The constraint functions, they are also majorants of gi at x of t. So in particular, this would mean that the constraint set of the subproblem would be contained inside the feasible region of the original feasible set. Original problem, sorry. So somehow we are doing inner approximations. And you can also see that each of these constraints actually correspond to a ball. And we are considering intersection of balls. So we are using intersection of balls, which can change from iteration to iteration to inner approximate the original feasible set. You can definitely think of this as a special case of the majorization minimization scheme. Well, because, well, this is majorizing. This one, we are also sort of majorizing because we are using a indicator function of a smaller set, which is definitely larger than the indicator function of the original feasible set. That's also a majorization. Now, this algorithm is well defined, and any accumulation point is stationary under MFCQ. Convergence of the whole sequence under convexity and semi-algebraicity is known. And of course, in practice, we don't really want to make use of the true Lipschitz continuity modulus. So there have been some variants with line search scheme. Now, before introducing our algorithm, I would like to point out that, well, the subproblem here is not necessarily easy to compute in general, except possibly for m equals 1. In this case, we are really just projecting onto one single ball. So that would be easy. Okay. And we are also really just considering one single inequality constraint in our noisy model. So this is our algorithm, which we call MBA L1, L2. So this is also a Dingleback type algorithm, like here. We are not making use of the quotient, but somehow the difference between the numerator and sort of a majorized version of the denominator. And for the constraint function, we are also majorizing. but we are majorizing the smooth part and the possibly non-smooth part differently. So for the P1, we make use of the Taylor's inequality. That's why you see this thing here. And for the minus P2, well, P2 is convex, so we take a subgradient and then subgradient inequality. And instead of making use of the true Lipschitz continuity modulus of the gradient of P1, we update it, we increase it until our X tilde is feasible for the original problem. Now, this algorithm is well defined in the sense that, well, each subproblem would have a unique solution, and this would not be a dead loop. Okay, so you will terminate after finitely many inner iterations. Okay, so algorithm is well defined. Slater condition holds for each subproblem. And we have the following standard type of subsequential convergence result, which says that, yeah, successive change is going to 0 and some nice form of stationarity condition. And if Q is also regular, which would be the case when Q is actually Lipschitz differentiable, well, which would be the case when we think of the Gaussian noise model and also the Quotient noise model, then X star, the accumulation point, is actually stationary in the usual sense. 0 belongs to the limiting subdifferential. So this is subsequential convergence. How about convergence of the whole sequence? Well, again, these days, convergence of the whole sequence would follow some very standard type of KL-based analysis. But somehow we will still need to figure out the correct potential function to make use of. And then everything will be routine. Now, the potential function we make use of in this case is something like this. Looks very complicated, but you can sort of identify the L1 over L2 here. And somehow I introduce this integrator function to rule out the origin. And definitely I do not want to change the problem. So I make sure that my rho is small enough so that it still contains the whole feasible set. Now for the constraint, this part is actually modeled after the convergence analysis in the paper by Botti and Powers, where they analyzed the global convergence of the MBA algorithm. So basically, we'll need to make use of what we exactly used in the subproblem, okay, which is we majorize the P1. Okay, and for the minus P2, it's non-smooth, but we can make use of the Young's inequality for the majorization. So that's why there's a conjugate over here. Now, a final piece of innovation is this thing, which would be the position for the Lipschitz continuity modulus, but we make it a variable to deal with the varying step size. Okay, the step size parameter that changes from iteration to iteration. Okay, then this is the global convergence result. So suppose in addition that P1 is C2. My P2 can still be non-smooth, but P1 has to be C2 because, well, when you take the gradient, the Hessian will pop out. Okay. Now, if if F tilde is a KL function, then we have convergence of the whole sequence. Okay, some numerical simulations, and because I'm lazy, I only do random instance. Okay, so this is the Cauchy noise model. We randomly generate a matrix A. I actually make the problem even easier by normalizing the column, and a k-sparse vector x tilde, and then a Cauchy noise vector. And I pretend that somehow I know some knowledge about my noise, so my sigma is sort of designed accordingly. Now, one thing about One thing about this L1 over L2 is that this kind of model is actually very sensitive to the choice of initial point. It's a very sensitive to the choice of initial point. So this was also observed in Yifei Lau's paper when they worked with the noiseless model. Okay, so they actually initialized their algorithm with the L1 solution, and here we also initialize our method using the L1 solution, except that the L1 model is also not convex. Yeah, okay, but doesn't matter. This is also the kind of constraint set that we can solve using MBA type method. So we use something we call SCP-LS, which is a MBA type algorithm variant that we studied recently. And we initialized at the least square solution, which is definitely feasible. And we terminate when successive fringes is small. And I will let you know what tolerance is in the next PPT. And this would be the problem size. Not very large. So my I would be just 2 up till 10. Okay. So N is the length of the signal. M is the number of measurements. Okay, less than the length of signal. Okay, so tolerance equals 10 to the minus 6 for both algorithms. Okay, so what I mean is I'm going to solve the L1 model, and then I get up till 10 to the minus 6, and then I get an X hat. I use this to initialize my L1 over L2. Yeah, and of course, my L1 over L2 is fast, but that's a lie because this is the total time, while including not just the L1 over L2, but also the L1 and also the time for generating A dagger B, which is the initial point of the L1. Okay. Now with L1 doing most of the work, but still the recovery error of the L1 model is not very good. Well, we always seem to improve using the L1 over L2, which is not too surprising because that's a non-convex model. Now, what happens if we do not solve the L1 model accurately? So we actually tried 10 to the minus 4, still seems okay. Okay, so this column would be significantly smaller, and then you still see something similar. But 10 to the minus 3 is tragic. So 10 to the minus 3 for the L1 model. Okay, now the L1 model is very fast, but it quickly returns some garbage. And because the initial point looks very garbage, we also only get some garbage. Well, although we are also improving, yeah, but it's not very good. Okay. Now the L1 over L2 seems very sensitive to this initial point, but then why do people still consider that? Well, one motivation for L1 over L2 is the fact that it is so-called scale invariant. So supposedly it should work for badly scaled instances. Okay, so we try to follow the experiment set up in the paper by Yifei Lau, where they only consider the noiseless case. Now we look at the noisy case as well, and let's say we just do the Gaussian noise model. But then we look at badly scaled instances, by which I mean there can be huge entries. Okay, so the D would be either 2 or 3. Okay, so it can be very huge entries. And I also use a very highly coherent columns. Okay, A that have very highly coherent columns. So if F is larger, then the compressed sensing problem will become harder. And of course, K is the number of non-zero entries. If we have more non-zero entries to recover, the problem would also become harder. Now, the good news is that now we are looking at Gaussian noise model, so we can use SPGL1 to solve the L1 problem. So you can see that, well, of course, SPGL1 is fast. Okay, and when the problems are like this, so when K and F and D are not too large, somehow, of course, we are still improving upon the L1 solution. But even for very hard instance, we are still getting pretty nice recovery error. Okay, although yeah, we take much longer time. Well, that's because the SPGL1 even failed to return something that's feasible. Okay. But this one we die completely. It's because the SPGL1 initial point is too bad. Okay. So I will quickly wrap up. So we established convergence rate of a Dinkelberg type algorithm for noiseless compressed sensing based on L1 over L2 minimization by looking at two different KL calculus rules for the fractional objectives. And then we look at algorithm for the noisy model. So yeah, future work. So yeah, Radu, Min, Dao, and Guoyin, they recently have some nice work on fractional programming. Yeah. So it will be interesting to see whether any of our results can be extended to their settings, in which they considered some of several fractional objectives. Okay. And also I mentioned KL type analysis for inexactly solved subproblems for the Dinkelberg type algorithm in the noiseless case. So that will be another interesting future work. So everything I discussed today can be found in this paper published in June. And that's all. Thank you for your attention.
Thank you very much, Ting Kei, for a very nice talk. A very impressive result. Are there questions?
I have, first of all, thank you very much, Ting Kei. It's very interesting talk. Of course, I like the MBA.
Yeah, you proposed the MBA.
So my question is related, in fact, in both. So in the first Dinkelberg type scheme, so you got only a theoretical result, in fact, right? I mean, this locally linear rate of convergence, but you don't have really an algorithm to compute the step, right? Do you? Or I'm
oh, you mean the noiseless
not this one,
model?
not this one. No. Yeah, the first
this one,
the
right?
part where you put, yeah, this one. So how do you solve the constraint step here?
Well, currently, well, basically, we adapt this algorithm from a recent work by Yifei Lou and basically her group. And in her work, they basically just use CVX and yeah, not very nice algorithm, just CVX interior point type method.
Yeah, but then
and I think later on they develop an ADMM approach. Yeah.
Okay, but then it doesn't stand with your theoretical. I mean, your result is asking for an exact. I mean,
this one is based on exact analysis.
Okay.
The inexact analysis will be much harder.
Yeah. Okay, fine. That's all.
Because
I wanted to be sure that I understood right. So fine.
Yeah,
I understand that.
Yeah, and because there are two non-smooth part here.
Yeah. Okay. Yeah. Okay. Yeah. And so in the second, can you show us again the MBA or the algorithm, the second algorithm when you're using it?
Yeah, this one.
Well, you have the final product somewhere. I don't remember. Yeah, this
one, the algorithm.
Yes. Okay. And so here you have only one constraint, right?
Right.
So basically, what you are so how do you solve this sub problem? It's easy.
Root finding procedure.
It's
just a root finding.
Okay.
I'm saying just a root finding, but it took my students 3 months to code it. There are a lot of cases. Yeah, because it's piecewise quadratic, but a lot of different cases. I think she divided that into like 8 different cases and then finally nails it.
But essentially, your constraint is just one ball, right?
Yeah, just one ball. Yes, just one ball. But this one is non-smooth, so somehow there's a prox going on, and then basically just a root finding.
And so this one you are capable to solve to high accuracy.
Yeah,
I see. Okay, so when you say you use the X tilde, it's an exact solution of the problem, more or less, right?
Yeah, that's the exact solution.
Okay. Well, very good, interesting. Thank you.
Yeah, thank you, Mark. Thank you. Are there other questions? Ting Kei, I have a question. Oh, we have another question, I guess. Yifei.
Oh, hi.
Hi.
Ting Kei. Can you hear me? I'm still.
Sure, we can hear you.
Okay. Okay, great. Yeah, thanks for the nice talk. I learned a lot from your listening the presentation. So I see in one of your slides you mentioned about the A inverse times B. So I just wondering, I guess you meant for a constraint, right? Not meant like A should be invertible.
Okay.
I don't know what's going on.
So Ting Kei, this was a question for you. We cannot hear you, Ting Kei. Oh, you are muted now. I'm not sure we can hear you, Ting Kei.
Yeah, he disappeared.
You should unmute him. He mutes himself. TK, you're mute.
Oh yeah, right. I think one of his screen is black.
Yeah, this is the iPad, I guess.
Yeah, I'm still playing with my iPad.
But So Ting Kei, can you hear us?
Radu, you cannot unmute. You cannot unmute.
No. Oh, he just. Oh, let's see what. He told me that there will be some broadcasting, and then probably he will not able to talk to us for 2 minutes. But this, like because of because of some officer. Okay, let me join again. Okay. So this was not the bad guy, just trying to make sure that you are not talking to us. So Ting, we're waiting for you since we have several good questions.
Hello.
Okay. Hi.
Yeah.
Welcome
Sorry.
back. Welcome back.
I think there's some problem with my iPad.
Okay.
And I sort of lose my slides.
Okay. No slides. No iPad. No slides. Okay.
Yeah.
Okay.
I can rejoin if we need to refer to the slides. Okay. Yeah. Sorry, Ife, I just missed you all everything you spoke.
Oh, okay. I just want to confirm that in one of your theoretical work, you have this delta of A inverting times B. I just want to make sure it's meant for constraint AX equal to B, not meant like A should be invertible, right?
Right. It's not A being invertible. It's just the constraint AX equals B.
Okay, and this constraint can extend to the noisy case, which is the like AX minus B smaller than the sigma type of constraint.
The KL result does not extend there. Sorry.
Oh, because it will include 0.
No, because the thing is not polyhedral. Yeah, the KL result only works when the A inverse B is when the feasible set is polyhedral. Okay, so it only works with the linear constraint, but not the box like circle. No. Unfortunately, no. I see. It's hard to prove. And thanks for mentioning so many times my work. Thank you very much. So I think I have 2 algorithms to minimize the L1 over L2. Have you compared with them? I know the algorithm is not good. I just want to see where does the stand not really, because we mainly look at the constrained version. I think we are solving very different problems. They are not quite equivalent. So I stick with the constrained version instead of the regularized version. Okay. Thank you. Yeah, I'm okay.
Thank you very much. Are there other questions?
Yeah, I can try to.
Ting Kei, I have a question and a remark. So first the question. So yeah. I mean, what I like very much is the Kyle exponent result of 1/2 for your for the objective function. But this is so fundamental for getting the good linear convergence. So is there any hope to extend, let's say, your problem formulation such that to preserve this result? I mean, what can one take instead of, let's say, the objective function you have now? Could you do some composition linear operators? Could you take other norms, or yeah?
Okay, so I'm not sure whether my voice is good enough now.
Yes, your voice is perfect. Okay.
Okay, so yeah, I would say that's a very hard question, because typically all the calculus rule that we may use of, I would say it's really like cheating, because when we do it in a non-convex setting, in the end, we always try to reduce to the piecewise linear quadratic case. So if we cannot find a nice base case to reduce to, then there's no hope to really extend or make use of those calculus rules to do any deduction.
Okay, understand. Yeah. Okay. Yes, but still, I mean, this is it's very important here to show this exponent, just to be able to current linear convergence. Then I have another observation. This is related to Mark's first question. So actually, all algorithms I know for fractional programming have this argmin term, which is always with respect to a set. In your case, it is a solution set of some linear system. I mean, it would be interesting just to try to formulate these methods such that, let's say one can combine the proc step, but a proc step over the whole space with a projection step onto this set. So this set you will always have in fractional programming. So there is no fractional programming over the whole space. You always have a feasible set, since you want to guarantee that the problem is well posed. Yeah? But then, are you aware of a method which just kind of tries to project on this feasible set, and then, of course, in combination with other evaluations? Yeah? Instead of this argmin step, which appear, also in my work and in other papers.
Oh, you mean just projection and then do some weird things?
Yes. Or first, or do at the end projection, do a real prox over the whole space and then project, or use some Douglas Rutherford or something like, which just allows you to provide a full splitting scheme. So this is something which was also mentioned by Mark. There is no real prox step or a proper prox step. It is the kind of argmin over linear system. And just to avoid either leaps, or to avoid,
Yeah, that I'm not sure.
Okay.
Yeah.
But I guess this is an interesting question, when addressing fractional programming problems. A kind of I mean, the algorithms are not yet full splitting methods. Because of this feasible set, which just appeared in the argmin problem.
Yeah.
Okay, but this is a good topic, I guess, for the future. So are there other questions?
Yeah, actually, I have one general question. I mean, how does this model, this ratio model, is doing regarding, in comparison to the formal problem, which is the L0 norm, essentially? I mean, yes, you are asking, basically, it's motivated by. That's what you talked about at the beginning with the spherical conditions that you had.
Yeah, the spherical section problem.
Basically, the original problem would be to minimize the L0 quasi-norm subject to linear constraints or subject to no.
Right.
So how does this model? I'm talking about the modeling. Do you know how good is this really approximation of? I mean, you mentioned the one of the results at the beginning when you look at the ratio of the L1 norm and the L2 norm. Is it better, for example, than using some sort of non-convex approximation of the L0 norm? Do you know?
I think in terms of recovery theory, in the recent paper that I just mentioned, that was published in Applied Computational Harmonic Analysis, that paper I mentioned in my slides. that I think they sort of proved a theoretical guarantee that is basically the same as the L1 so far. So in terms of theoretical advances, the L1 over L2 is still lagging behind somehow. Yeah.
I see. Okay. So yeah, okay. But then, okay, so then the first result that you mentioned, the theoretical result, I mean, you have to check this condition on the kernel. That's not necessarily easy to check this.
Oh, that's not for checking. It's like that thing is something like RIP that you never check it.
Yeah, that's the same style, right?
Yeah, same style, yeah.
Okay. No free lunch.
Right.
Never. There is never free lunch, Mark.
So, yes, there is some time to time you can find some free lunch. You have to find them.
Yes.
You have to find the address. Okay, very good. Thank you, TK. Very good.
Very good. Thank you, Mark.
Thank you.
Are there other questions? So there are no other questions. So then we can stop here, Ting Kei. Thank you very much for a great talk.
Okay, yeah. Thanks for your invitation
answering
again.
our questions. So we will post the slides and the video on our website. And I just want to announce that our next speaker will be Peter Ochs from the University of Tübingen. If I'm not wrong, but let me check this just not to say something which is not correct. Yeah, Tübingen is correct, from Germany. So Peter Ochs is our next speaker. I wish you a nice week. Yeah, see you next Monday. Thank you, Ting Kei. It was great. Thank you very much.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.